All right, so my name is Billy O'Neill. I work on the Microsoft Standard Library implementation. My PM friends have asked us to tell you that we have a booth, which you've probably all seen on your way to the various keynotes, and we're doing this survey that you can fill out and potentially win an Xbox at Herb's talk at the end of the week. So I work on this thing, the standard library implementation we just announced. We are taking open source under libc++'s license. We announced this yesterday at 4 o'clock. Oh, too far. All right, so this talk is basically, this talk boiled down to its parts is go to the list of papers that have been voted in and actually look at all of them, not just the ones that people give giant talks about, because there are lots of features that go through the committee and that have people spending a whole bunch of time on that aren't necessarily headline things that you go rewrite big hunks of your code base for. So when you go deploy concepts into your code base, that's going to be universe altering, just like say R value references were, whereas these are all things that you can put into one place and you can improve that one place and you don't need to redefine the universe. So I'm going to start with feature test macros. I know I said that this was a library focused talk, and a lot of the point of feature test macros is for core stuff. But I wanted to include this because you might want to know if you can use any of these features that I'm going to be talking about. And this is a way that these are officially added in C++20, but implementations are adding them for previous language modes because that's the whole point of being able to ask if this feature is present. And I include this because I've taken this example directly out of the standard, and it's not entirely obvious why you might need these things because, well, we added has include, and so you can now ask, well, if there's a header named optional, that of course means you can use the optional type. Well, not quite, and the reason for that is because compilers have language mode switches. So if you say include optional, or if you say has include optional, then include optional, but your compiler is in C++14 mode, well, the optional header will act like it's empty. So just saying is the header here is insufficient, and that's one of the reasons why we added this. All right, next, really basic. I can't believe it took us 20 years to get the ability to ask if a string starts or ends with something, but you can say, hey string view, do you start or end with something? And if it's a string view, you can even do this at const expert times. You can say static assert that this thing starts or ends with, or doesn't start or doesn't end with the thing. So that one's really basic. Here's somewhat more different, and I included this because I've written one of these in every single code base that I worked on before I worked on the standard library implementation. So stood clamp. So what clamp does is it gives you effectively saturated behavior for numbers. So you say, I want this value to be in between these two other values, and if the supplied value is outside the range in either direction, you will saturate on the end of the range. So here, all three of these clamp calls are clamping the input between 10 and 20. And so 1, 2, 3, 4 is bigger than 20, and so the result here, A, is 20. 11 is within the range, and so it doesn't need to be adjusted at all, and so the result B is 11. And 0 is less than the range, 10 to 20, and so the result is 10. All right, exchange. This one is, people always forget about this one for some reason, because they go, well, I could just use stood move to do this. So what exchange does is it's a function that takes a reference to a value, like a field or something like this, and what you want to assign over it, and it returns whatever the old value was. And if you look at an actual implementation like this is actually what our implementation looks like, except I've de-uglified some of the variable names. You might be wondering, why are these static casts here, and what's going on with this? So the big reason why you might want to use exchange in your code base is it does the same thing stood move does in this application, but it resolves a safety problem with move. Because when you use move on this example, you end up with the variable being in a move from, right. It's fine. You end up with the variable being in a move from state, and then you can accidentally touch the move from state, and sometimes that's okay, depending on what your type is. but sometimes it isn't, and you touch unique putters that are empty and nulled out and things like this. Also, there's not even a debug code gen cost for this. So like, even if you're not turning the optimizer on, and I need to stop doing that. Even if you're not turning the optimizer on, you get this for free because you would have been writing the std move call to do this anyway. So there's still exactly one function call, just like before. But in addition to this code is now shorter, this code also no longer leaves the member in a state where you might accidentally touch it in a move from condition. All right, this is fun stuff. In C++11, we got StandLock, which is an algorithm that you give a whole bunch of lockable things, and they're lockable things if they have a member named lock, a member named try-lock, and a member named unlock. So you could make wrappers that are like, well, of course, std mutex already has this interface, and std shared mutex already has this interface. But you could write a wrapper around, say, Win32 semaphores, or critical sections, or kernel primitives if they have the associated try-lock bits. And what's neat about StandLock is it doesn't need to like reach into the scheduler to do this. Like, it will take all of the locks that you supplied, and it will do that in a way that doesn't deadlock your program. And it just does this by choosing the right ordering of lock and try-lock and unlock calls. And so, for example, let's say you're doing some kind of data processing, and you want to manipulate two values at once. And I've used swap in this example because while atomic exchange is something that you could do as an atomic operation, there are no atomic operations that talk to two different memory locations. So if you wanted to swap these values, you would need to take both of the mutexes, just like this scope lock does. And this is the new feature in 17 is not StandLock, the algorithm, it's scope lock, which gives you a nice RII interface for this. So here, this will take both of the mutexes on the two data members, A and B, and then you can do your swap knowing that all of these operations are protected by the mutexes, and then the mutexes will be unlocked for you when the scope is exited. And if you've written a lot of this kind of code before, you might be going, well, why do I need this fancy standard library magic sauce to decide which order to take these locks in? Like, I can just pick an order, and as long as I lock them in the same order, that will do the right thing, because that's the classic example for this problem. Well, you could do that, but Howard Hinnant is one of the original maintainers of the libc++ standard library implementation, and he is smarter than all of us. I'm sorry? Maybe combined, yes. So if you, this graph might be a little too tiny for people to read, I apologize. So this is an example where he had some threads that were doing like 30 seconds of work, and they needed to take two mutexes to do that work. And the blue line at the bottom is like the theoretical minimum time it could take. And the green line that's like slowly growing off the end of the chart is what happens if you choose the handwritten ordered blocking thing. And Howard has really awesome, we're going to see if this works. Really awesome, no, it's not going to work. 1 second. Did that work? Howard has really awesome videos on his website that sort of explain how this works. Is that working? Yes. Okay, so here, if you had written the ordered thing by hand, this is going to discover that we have 4 threads and 4 mutexes, and so theoretically, 2 of the threads should be able to make progress here. But if you just choose the ordered thing that people do by hand instead of using something like StandLock, well, a whole bunch of our threads are blocked and unable to make progress. And what StandLock can do, if I can find my pointer, is it will do the same thing. It will go through and do basically the same thing the ordered locking strategy would do. But once it has discovered that the 0th thread is able to make progress, instead of just blocking everything else, the other threads keep going and try to find additional non-colliding domains to make forward progress. So here, and this is why StandLock can do better than you would do by hand if you were just writing lock calls in the right order. And if you want incredible detail on why and how this crazy magic stuff works, if you go to Howard's page, which I have linked to, I've included all of these slides in a GitHub repository, and the code examples I will link to at the end of the talk. But Howard's page here has all of the nitty-gritty on how this works. No. All right. All right, is that working? All right. Next thing, parallel algorithms. So this is kind of close to the edge of the theme of this talk being like underrepresented things that people talked about at talks, because I talked about this last year. So, and I've also written blog posts and stuff about this because I implemented big hunks of our Visual C++'s parallel algorithms implementation. But the reason I want to include this is even in my talk last year, I had examples that showed like the parallel algorithms only win for ridiculous n. Like n is hundreds of thousands or millions. So to demonstrate, I have an example benchmark program that just takes a vector, it fills it with random garbage, and then it times how long it takes to sort that. And if you run this program, let's see here. I've included this program in the GitHub repo, and those numbers are way too tiny for anybody to read, and that's not the problem. The thing is, this is what you get for how long serial sort takes versus parallel sort. And you can see that even with the optimizer disabled and everything else, the parallel sort catches up with the serial sort when you account for like the overhead of parallelizing this at around only 1,000 elements. And you probably have things in your program that want to sort 1,000 things. Like that's not ridiculous values of n. And the reason that sort is usually a good example to use for this is because sort does more than n work. It does n log n work. And so even with fairly reasonable values, you can get reasonable speedups with this. I also want to point out, I've included a previous parallel algorithms implementation that we used to ship, or we still ship with Visual C++, but we recommend you not use, and this is one of the reasons why. The PPL parallel sort algorithm is 16 times slower than serial with the optimizer disabled. And you can see it's exactly the same as serial up to about 2,000 elements, and the reason for that is they have a check of if n is less than 2,000, call the serial std sort algorithm. So if you turn on the optimizer, my remote is not working. Oh, there it goes. If you turn on the optimizer, this moves up a little bit. Because I'm testing with unsigned ints, which are like the cheapest comparison operator you could think of, you need more elements for the parallel version to win, and PPL does fix itself. And you might even be looking at this and going, well, you tested this on a machine you tested this on a 2990WX with 32 cores. Like, well, maybe that's an unrealistic thing for my customers. Maybe they only have 4 cores. Well, if I run this with the optimizer turned on my laptop, the same one that I'm giving a presentation on right now, the point actually moves back down. So even with smaller numbers of cores, the win still seems to be at around 1,000 elements. So you probably can get value out of this, even if you're not dealing with like HPC scale, like working with gigabytes at a time workloads. Because here, you're talking 1,000 integers, that fits in L1, right? All right, so that was very deep into features. Let's go back to really tiny basic ones for a moment. Contains. So the associative containers in the library have always had a way to ask, is the element in the container? So that went too far, sorry. So previously, you could have said, find this element, and if it's in the container, and you could tell if it was in the container by comparing the result of find against end. And people don't like this because I've specifically chosen the variable name to be one letter so that it fits on the slide. But if you have like reasonable names for your container, this turns out to be kind of a lot of boilerplate just to ask if the element is in the container. And sometimes people would try to work around this. They use the count member on the associative containers, and they would compare that with 0. And the unfortunate part of that is standard libraries didn't optimize the count function very much, because until somebody came to us with this, it was not obvious why you would even ever use that. And if you have a multi-container, like a multi-set instead of a set, it actually has to do more work because it doesn't have to just ask, are you in there? It has to also visit every element in the container that matches the value you passed in. And that's unfortunate to get worse runtime performance to avoid typing not equals end. So in 20, we added contains, which does the same thing the not equals to end does, but now doesn't make you write all that boilerplate. All right. Okay, so splicing maps and sets. This is the feature that convinced me to write this talk in the first place, because it's not a small feature, but it's a feature that I didn't see anybody talking about. So the standard library containers are broadly divided into these node-based and not node-based forms. So node-based containers like list and forward list and the associative containers allocate each element in the container in their own individual memory blocks. And Deck might do that sometimes if T is really big or something. So that means that you can change the order of elements in the container without actually moving the elements in the container. You just change the pointers around in the container to point in a different order. So for example, when you call list sort doesn't move any elements. It just changes pointers around so that the elements appear in a different order. And so I want to give you sort of a mental model of what do the node-based containers look like. So I'm sure everybody can figure out what this is. This is a list. And I've also included in grayed out arrows here extra pointers that the Visual C++ implementation specifically has that the standard doesn't make us have, but we do. And sometimes it's helpful and sometimes it's not. But anyway, so for list, you have your elements, and they're connected by forward and backward pointers. And our list is circularly linked. So you have this end sentinel node that becomes the end not dereferenceable thing. And forward list does the same thing, except it changes the end sentinel to go to the head. And you would think that you could do all of the things. I'm just going to put this remote down. All right. You would think that, well, the associative containers, like tree-based containers, set and map, you would think you could remove one of these elements and pass them around just like you can with list splice or list merge. Because, well, it's a separate allocation. Why would you need to copy the data out of these? And you might have this image of what a hash table looks like, and you would think that you could extract one of the nodes out of there like this. And this is what the classic computer science example of a hash table would look like, but I regret to inform you that the standard unordered containers don't actually look like this. They look like this, which people look at a little bit and they become unhappy about. So if you hear people talk about the unordered containers and performance problems that result of that, well, that's because what's actually going on here is this is a stood list. Think of the unordered containers like you think of stood lists, because they behave just like stood lists. That's how the begin and end iterators for them work. And when you do lookups in them, it's just finding the right place in the lists. There are somewhat different data structures about this. So in the Visual C++ implementation, why does that keep happening? I'm not even holding the remote this time. I guess, maybe. All right. So in the Visual C++ implementation, it is actually a vector and a list inside. There are other implementations where they have purpose-built data structures, but the point is the nodes have to be separately allocated because rehashing the container or inserting things into the container don't invalidate pointers to the elements. So it has to behave like a list in that sense. And it needs to be iterable, so you have nodes and you have pointers, and so it's going to look like a list or a forward list somewhere underneath. But you can't just suck one of these nodes out of the containers because the associative containers have container invariants that they need to maintain. So the tree-based containers need to remain being a balanced binary tree that's ordered by the key. And the unordered containers need the hash functions and stuff to be correct so that it can find the elements when you go to look at them. And so you can't use a list of one element as the thing you use to like splice an element out of one container and then splice it back into another container in a different place. So in C++17, we had to add a new thing that kind of acts like a container iterator. So the associative containers now have this container : node type, which you would access just like the iterator type. And when you make one of these, it has a pointer to an extracted node and an allocator for it. So if you destroy the node handle, if you destroy the node type, before you've inserted the node back into a container, we need the allocator to deallocate it. And because the element is no longer in a container, you can do interesting things that would invalidate the container's normal guarantees. So this is an example that I took out of the compiler and removed a whole bunch of code from to fit on a slide and changed some of the variable names and stuff. They were doing this horrible undefined behavior thing where they had a map of things and they wanted to change the key in the map of things. And so they needed this const cast to do that, because when you use one of the associative containers, like map or unordered map, the keys are consts. And the keys are consts because if you could change the key without telling the container, you could make the container not be ordered anymore. Or you could make the hash of the container of that element different, which would be a problem. So instead of doing this undefined behavior thing and causing bugs that take literally weeks to find, like this one, what you can do now is you can extract the element out of the container, and this gives you that node handle type. So in this example, the auto moved entry is that container : node underscore type. And so this thing is sort of logically a pointer to the extracted memory chunk. And because it's extracted out of the container, it doesn't need to meet the container's invariance anymore. So you can write over the key. And in particular, you can write over the key without changing any of the pointers elsewhere in the program that refer to this. Like the reason the compiler was doing this const cast before is because they had all kinds of pointers to This is a comedy routine, I swear. They had all kinds of pointers to these entries that would be broken if they had actually tried to reallocate the entry. So now you can extract it, change the key all you want, and then reinsert it. And when you do that, you've told the container that you've done this potentially invalidating thing. And if you, for example, if you change the sort order, the container will fix it and it will put the element where it goes without allocating or anything like this. All right. And one cool part of this is that's also extended to merge. Sorry?
I'll ask you.
Okay.
Okay.
Okay. So one cool thing about this is that's also extended to merges. So you can do set operations. So you could use vectors and std set difference and things like this, but you can do merge just like you could merge two sorted lists into an overall still sorted list on list and forward list. You can merge the associative containers, and the elements that are in one of the containers but not in the other one of the containers will be spliced over effectively. So here, if we were to run this program, we have the element, let's see here, the element -1 in set 2 is not in set 1. So the element -1 is going to be spliced over into set 1 by this set1.merge set2 call. And this splice happens without physically changing the memory address of the -1 in this case. But if you look at 2, 2 was already in set 1. So because that element was in both sets, when you call merge, it's left alone. It stays in the source set. So if you want to answer the question, tell me the entries in this set that were already present in this other set, if you're okay with merging them together like this, this might be better, depending on what your data looks like and all that kind of stuff, to answer questions like this. All right, last thing. So in C++14, we added this unordered transparency feature where you could take a container like std map, like map of strings, and you could say less of empty diamonds, and that would tell the container, I want transparent lookup. So that went too far. What? I apologize. So you could have an example like this, and you have a container of strings, and you want to look up the location in the container of strings for a string literal. And then the first time you'd call find, that would allocate memory, because it would have to make a std string here, which would be unfortunate. And if you had a string view, it doesn't even compile, because the conversion from string view to string is explicit. And if you make it compile by casting it to string here, then, well, it compiles, but it's still implicitly allocating, or it's not implicitly, it's still allocating a string here when you didn't necessarily need to. But if you take that and you just add less empty diamonds, that says, I am okay with this opted-in transparent comparison, and it will pass the less than comparison from the parameter that you pass to find or extract all the way down. So this will end up calling the less than operator of std string and the const char star. So that was C++14. The new feature in 20 is The new feature in 20 is you could have done that before with the ordered containers, but lots of people use the unordered containers. So now you can give the unordered containers a special hash function, and the special hash function will say, hey, I have this transparent key equal type def inside. And if you do that, that tells the unordered containers, you can pass arbitrary t into me, and that's fine. So in this example, I have a hasher, and the hasher can hash anything that's convertible to string view, and it will use the equality comparison operator that string view also has by using equal to empty diamonds. So now you can do the same thing with the unordered set example. You can have your unordered set of strings with this special hash function, and then you can find the const char star without having to allocate a temporary string to answer the question. And similarly, if you convert it to a string view first, then you avoid the strlen on the potential strlen on every comparison. So, Marshall, I think you had a question. Okay. Any other questions? Can you go ahead?
Can you please open a slide with the merge of the two sets?
This one.
Yes, in the lowermost comment, the element with value 3. Can you tell me about that element?
See, when I originally wrote this, I had actual program output, and people were like, "No, you should write it as a comment on the slide." And I apparently can't type. I apologize. That's wrong. What should that be? 4. Yeah.
Okay.
Yeah, it should be 4.
And can you open the slide with the hash table?
This one?
Yes. You said that it's iterable, which
Yes.
means that it should have an iterator begin. What does iterator
Yes.
begin point to?
At least-
Where that is
So in the Visual C++ implementation, begin points at. Let's see if I can PowerPoint this thing. Begin points at this node.
But where that pointer is stored, how is that pointer determined, calculated?
So the container has a list inside.
Explicitly, that
Plus,
pointer
it
is
has
explicitly
a std list
stored.
inside. It's a variable of type std list and a variable of type std vector inside the std unordered.
Okay, thank you.
I have a question and a comment. First, does clamp work only for numeric type or arithmetic types?
So all of the use cases I've ever had for it have been numeric types. I think it works with other types.
Yeah.
I have not tried that myself.
Looks like Marshall has an answer.
I know because this was my proposal. There are two versions of std clamp. One of them uses operator less than. The other one uses a comparator you pass yourself.
Right.
And
So
from the recording, Marshall
yeah.
says that was his proposal, and that there are two versions of clamp, and one of them accepts an arbitrary comparison object that works with things that are not numeric types.
Yeah. And my comment for your std sort example, your parallel std sort example, since it was integers and a built-in comparison, if you do a parallel radix sort, I bet it'll be faster. Yeah,
Your standard library implementation might do a parallel radix sort for that. Yes.
Thank you for the talk. My question is with regards to your statement that count on the associative containers
Yes.
is not as efficient. I can understand that for the multi prefix containers, but my understanding was for the hash maps and like set and map, those had the same time complexity as just a lookup. So if you did .count on a set, it's going to return 1.
So
but you're saying that it's less
the
efficient
big
potentially?
O of count is order of the count. So the big O of find, because count will always be 0 or 1,
Right.
because it's not a multi-container. The big O complexity will in fact be order of 0 or
Okay.
order of 1. However, standard library implementers didn't know about this pattern until relatively recently. And so
Really?
standard library implementers implemented count as call equal range and then call distance on the result.
Wow.
Because that's for the multi-containers, that's like, as far as most of us knew, the only use of this thing was on the multi-containers. And so we didn't optimize it very much. So in fact, as part of implementing contains, at least in the Visual C++ implementation, we fixed this at the same time.
So, but just to be clear, on the non-multi containers, it was as efficient as a lookup. It was just on the multi ones.
No. It was 2 lookups.
Okay.
It was because
So the time
because
complexity
we did
was
equal
this-
range. Equal range has to find the
Right.
beginning and end.
Twice.
And we didn't special case I know it's a unique container, and so I can avoid the second lookup.
That's very interesting. Thank you. And I think Ben has
And it was a bug, and we fixed it, and we're sorry.
It's okay. It's okay. Thank you. Thank you for the response.
The comment was that count was explicitly recommended for this case by Scott Myers in Effective STL, and again, I guess I have no choice but to apologize. We fixed it now.